Okay, in this video, we are doing Calc AB Midterm Review Part 2, but I think it'd be fair to say that we're really just going over Unit 5 of Calc AB. So I have here like the list of all the topics that are in Unit 5. I didn't think I hit these very hard in the first part of the review, so I wanted to come back and do it again. So we're definitely, not in order, but we are definitely doing this. We're definitely doing this. Determine intervals, yep. First derivative test, I'm sure we're going to use candidates test. I'm pretty confident is in there. Concavity, yes. Second derivative test, almost unavoidable. Sketching graphs of functions and their derivatives. I think I'm going to come back in a different video and do some of this. Connecting a function. I mean, this is in here. I think I could do a better job maybe in another video. Some optimization for sure. We're going to solve some. And then this is not so much in here, but this was in the first one, and I have a lot of other videos about it. A word on that, we're going to be doing a lot of problems. I have a lot of videos where I've gone into detail about, how to use the concepts, what the concepts are, what they say, and what they mean. So I would definitely recommend that you look at the links below, or I'll create a separate playlist, and you can take a look at that. So let's do some problems. All right, so. All right, this will be problem number 1. Not really sure where it came from. I think I wrote it, but who could really say? We want to find all the asymptotes of, so I'm going to need this function. So I'm going to handwrite it and then like copy and paste that. So 3x minus 2 e to the 3x minus 2. All right, so let me, just going to like have this available when I need it. So copy. All right, here we go. Find all the asymptotes of the function. So asymptotes, I think everyone immediately thinks of vertical asymptotes. So vertical asymptotes, we would need the denominator, e to the 3x minus 2, to equal 0, but this does not equal 0 because e to the 3x minus 2 is always greater than 0. So we're going to have no vertical asymptotes. All right, which brings us to the question of horizontal asymptotes. So we need to look at the limit as x approaches infinity of our function, which is 3x minus 2 over e to the 3x minus 2. So I'm going to use relative growth rates. Relative growth rates. And by that I mean an exponential is going to destroy a polynomial as you go to infinity. So you could also use L'Hopital's rule because you do get infinity over infinity by like direct substitution. But I'm going to use relative growth rates and just say that this is equal to 0, which means that y equals 0 is a horizontal asymptote. So that's one answer. And then because this is not a rational function, we do need to worry about going to negative infinity. So limit as x approaches negative infinity of 3x minus 2 over e to the 3x minus 2. Now, if you think about this one, by direct-ish substitution, so I'm walking you through what I, like in my mind, what I think of this. This is going to go toward, the numerator goes to negative infinity, and then the denominator is going to go to e to the negative infinity, but now you have to like think, what does that mean? Because e to the negative infinity is like 1 over e to the infinity, which means this is going toward negative infinity times e to the infinity, which goes toward negative infinity, which is not a finite value. So there's no horizontal asymptote as you go this way. So there's no horizontal asymptote to negative infinity. So the only asymptote that we get in this problem is actually this one. All right, and I mean that happens. That's okay. Next up, find the intervals on which f of x is increasing. So increasing, you like have to immediately think to yourself, I don't remember if I copied that. I like to duplicate. I know it's like weird. I just enjoy dragging things around. As soon as you're increasing, decreasing, you think first derivative, concave up, concave down, you have to think second derivative. So for b, we're going to find f prime of x. Let's go. Quotient rule. Bottom, e to the 3x minus 2. Derivative of the top, minus top, 3x minus 2. use your parentheses. You will make far fewer mistakes. That all over bottom squared. All right, now this cleans up because we can take bottom derivative top minus top derivative bottom. I forgot to multiply, I forgot my chain rule. There we go. Okay, so I can take out 3e to the whatever, 3x minus 2. That gives me 1 minus 3x plus 2, because I'm distributing the negative, over e to the 3x minus 2 squared. So we can cancel an e to the 3x minus 2 and get, if we combine this, f prime of x is going to be 3. I mean, it's 3, and I'll just write it like this. 3 minus 3x. So I could take out a 3 and have 9 and then 1 minus x. And then e to the 3x minus 2, because we canceled 1. 9, 1 minus x. You might take out negative 9. I don't like to actually take out a negative because I make more mistakes when I do that. All right, we're gonna have to do a sign chart. So this is the first derivative test that we're really using on this. We're gonna look at sign changes in the first derivative and use them to tell us if we've got a maximum, minimum, or perhaps neither. So critical points will be when f prime equals 0. So critical point, f prime equals 0, or is undefined, n has to be in the domain, but in this particular case, all we have is equal to 0. So that'll be when x is 1. If we plug in negative a billion, we get positive, so increasing the entire way until we get to 1. If you plug in a billion, you get negative. So that means that f is in, what are we answering? Increasing. F of x is increasing on, let's say that, I'm going to flip this. So I'm going to say because f prime of x is greater than 0 for x less than 1, f of x is increasing on negative infinity to 1, and I'm going to count 1. There we go. So that's my answer. So negative infinity to 1. All right, the next part, intervals on which f of x is concave down. We're going to need f double prime. I'm going to need another page. So let me insert, add a page. All right, and then I'm also going to copy this because this is f prime. Duplicate. Okay. Done with you. Go away. All right, f prime of x is this. So f double prime. Bottom. Derivative of the top is negative 9 minus top, which is 9, 1 minus x. Derivative of the bottom is 3e to the 3x minus 2, because I might forget the chain rule once, but not twice. Bottom squared. Okay, so this, again, we can take out, ooh, what is Siri doing? Stop listening to me. Yeah, you don't understand. You don't need to listen. All right, we can take out E3, 9. You can take out 9. I'm going to take out 9 e to the 9 e to the 3x minus 2 gives me negative 1. I'm going to write minus 3 and then 1 minus x because I'm a little worried about how many negative signs are going on here. And then e to the 3x minus 2 squared, holy cow. 9, e to the 3x minus 2 cancels. This will give me negative 1 minus 3 is negative 4 plus 3x over e to the 3x minus 2. Holy cow. Is this a good problem? I don't really even know. I'm like, how much space have I used? Quite a bit. F prime of x, f double prime of x. All right, sign chart. Because in this one, we're looking for concave something. The only place this is 0 is at 4/3. Okay, so then if I plug in negative a billion, I get a negative. If I plug in positive a billion, I get a positive. So we were looking for concave down. All right, so we will say f of x is concave down on negative infinity to 4/3. I'm gonna do open interval, and then we'll say because f double prime less than 0 there. Okay, so that's that. And then for the next one, what I think I'm going to do is find any intervals on which f of x is both decreasing and concave up. So decreasing concave up, so this is, I don't know what this is, A, B, C, maybe C, D. This is a long problem. D. Now I can't even remember. Decreasing concave up. Okay, so if we think about it, we had f prime, which was at 1. We have f double prime, which is at 4/3, which is greater than 1, which is super relevant. So this went this, and I'm pretty sure this went like this. Okay, so we want decrease. I should have spaced this out more. Decreasing concave up. Decreasing concave up. So we will say f of x is decreasing concave up for x. So we want decreasing, which is like all of this, concave up, which is all of this. So we got to go past 4/3. So for x greater than 4/3, and our reason is because f prime of x is less than 0, and f double prime of x is greater than 0 on that interval. Whew. Okay, that's the problem. All right, let's see the second one. I think I wrote this too, so it's probably terrible. Let's find out. Let h of x be a differentiable function satisfying h of negative 2 is 5, h prime of negative 2 is 0, h double prime of negative 2 is 8. Does h of x have a relative minimum, maximum, or neither at x equals negative 2? So let's think about this information. We know that h prime is 0 and h double prime is greater than 0. So h prime is 0. So you have a horizontal tangent line and your concave up. Let's draw a picture there. Second derivative test tells us that you have a relative minimum. So I'm going to say, since h prime of negative 2 equals 0, and h double prime of negative 2 is greater than 0, h of x has a relative minimum at x equals negative 2. Often you don't cite the second derivative test, but I'm going to say by second derivative test. Because, I mean, that's why. Right? So draw a figure can really help. Don't be afraid to draw. Like, I see a lot of people just sit there trying to, like, think through an answer. Why just think it through when you can draw a picture and just, like, have the answer immediately? All right, let's see what the third question is. All right, this is 1991 BC2. So f of x is x e to the 1 minus x. We want to find where f is increasing. We want to find the range. We want to find the x coordinate of each point of inflection. All right, here we go. Increasing, immediately I think first derivative. So I'm going to find that. F prime of x is first derivative of the second, e to the 1 minus x times negative 1, plus second, e to the 1 minus x, derivative of the first, which is 1. All right, always a good idea to factor this if you can. I'm going to take out e to the 1 minus x, which leaves me with It's like negative x and then plus 1, so I'm going to write 1 minus x, which keeps happening. So this is f prime of x. All right, the only 0 of this, because e to anything is going to be greater than 0, or never 0 at least. So the only 0 of this, the only critical point, is at 1. So we will sign chart this. So I'm in f prime of x equals 0. X is 1. So we'll put 1 f prime. If we plug in negative a billion, we get a positive. So you'll notice I always go really extreme. I don't go close to the number. If I can, like negative a billion and a billion, it's very clear what's going on. Highly recommend that you do that. Don't like get like, you could plug in 0.9, but then you might have to think about it. Negative a billion is obviously going to give us 1 plus a huge number. That's definitely positive. E to the 1 minus x is not contributing anything, so I'm kind of just ignoring it. Plug in a billion, and we get a negative. So f of x is increasing on x less than, or say less than or equal to 1. You could say just less than. I'm pretty sure you would get all the points on an AP exam. And then my reason is because f prime of x is greater than 0 for x less than 1. All right, find the range. Okay, so let's think this through. F of x increases forever until you get to 1, and then decreases forever after 1, which means that if we were to graph this, we're kind of dealing, we might be dealing with this. We might be dealing with this, where this just keeps going forever. Well, we couldn't have this, so it might do this, like increase, like subtly increase, and then decrease forever. So we got to figure out what's going on as we go toward negative infinity. And then we also need to know what's happening at 1. So you have a relative, I mean, it doesn't say to give a reason, but I'm going to say that f prime changes positive to negative at x equals 1. Therefore, f has relative maximum at x equals 1. All right, so we know that there's a relative maximum. It's actually the absolute maximum because it's the only critical point and you have a relative maximum. So absolute max at x equals 1 because only critical point and relative max. So that's the only or lonely critical point theorem. If you have only one critical point and a relative maximum there, you must have the absolute maximum. Now I gotta look at, as we go to negative infinity, what's going on, right? So like my thought process is I might have a graph that looks like this, or I might just have a graph that looks like this, right? Like one of those could happen. So if this is the one that's happening, then my range is negative infinity to whatever I get here. If I have this one, then my range is, well, actually, it's probably still going to be negative infinity. I do have to look at as I go to infinity. So I have to look at both of those limits. So let's do the limit as x approaches negative infinity of, what is our function? X e to the 1 minus x. E to the 1 minus x is infinity times e to the negative infinity. That's 0, I'm pretty sure. Like, think, oh no, actually this is negative infinity e to the infinity. This is very negative infinity. Okay, but we really shouldn't put equal signs there now that we've like worked out what we're doing. So let's like move this down here. This is our thought process, so we'll just like put this here, and we'll say negative infinity, right? Like it didn't happen. So that's negative infinity. So if that's negative infinity, it doesn't matter what it's doing on the right-hand side of 1. Like that's all we got. So f of 1 is our absolute max, which will be 1 e to the 0, which is 1. So the range is going to be negative infinity to 1. and you definitely get 1. So that's our range. So it's important, though, that you like think about behavior at negative infinity and infinity when you're talking about range if you have an absolute maximum, because it could be important. There's a third option where you have like this, right? Like that could happen. Maybe there's a fourth option where you go like, right? So any of those could happen. So we really need to look at negative and positive infinity. And find the x-coordinate of the points of inflection or the point of inflection or whatever. So f prime, let's copy and paste. F prime, we got this. Super hinged upon having gotten that right, but I don't know. I think I felt good about that. So let's see. This is f prime. So f double prime. First derivative of the second is -1, not negative x. Plus second derivative of the first, which will be e to the 1 minus x times -1. All right, what can we do? We can take out negative e to the 1 minus x, which will leave us with 1 plus 1 minus x, negative e to the 1 minus x, 2 minus x. All right, so we need to do a sign chart. I mean, you can tell like x equals 2 is the only possibility. 0, x is 2, sign chart, put 2, f double prime. We just need a sign change, right? So if we plug in negative a billion, we get negative and then positive, so negative overall. And then if we plug in a billion, we get negative, and then we get negative, so positive overall. So I'm going to say over here, I guess, f of x has POI at x equals 2 because f double prime changes sign there. All right, it's a good question. So take a look at that, see if your work matches or whatever. If you're just watching, I don't know, I guess it would obviously match. All right, let's move on to number 4. This is 1992 BC4. F of x is this piecewise function defined above. For what values of k and p will the function f be continuous and differentiable at x equals 1? Okay, so continuous, we need the limit from the left as x approaches 1 from the left to equal the limit as x approaches 1 from the right to equal f of 1. Those are the rules. So the limit from, because of this definition, the limit from the left and f of 1 will be the same, and they will both be equal to, plug 1 in here, 2 minus 1. They're both equal to 1. So this tells us that 1 is equal to, the limit from the right will be when we plug 1 in here, which is 1 plus k plus p. 1 plus k plus p. So k plus p is 0. All right, differentiable. We're first going to find the derivative of each branch. And so you want to like just fly through this process basically, because we need to like move on, right? So don't include this, right? Because we're trying to make it differentiable. We don't actually know if it is. And then this will be 2x plus k. The derivative of p is 0 because p is a constant, greater than 1. All right, so we need, basically you need f prime of 1 from the left to equal f prime of 1 from the right, which tells us f prime of 1 from the left is when you plug 1 in here, which is 0, equals f prime of 1 from the right is when you plug 1 in here, so 2 plus k. So k is -2, and if k is -2 and k plus p is 0, so this is going to tell us that p is 2. Okay. So we have that. For what values of K and P, no, for the values of K and P found in part A, on what intervals is F increasing? So let's write this thing. So F of X is 2x minus x squared when x is less than or equal to 1, and then it's x squared minus 2x plus 2. X squared minus 2x plus 2 when x is greater than 1. And we're looking for when this thing is increasing. So let's find f prime, which is 2 minus 2x. Now we can include it, and we can actually include one on either branch because we made this thing differentiable. So like you have to get 0 at x equals 1 for both of them. And then this will be 2x minus 2 when x is greater than 1. And you can see if you plug in 1 for both of them, you get 0 here and you get 0 here. So that makes sense. Now, sign chart. Okay, sign chart. All right, so f prime of x equals 0. I mean, I know I keep saying sign chart, but f prime of x equals 0 would mean 2 minus 2x equals 0, x is 1, and then 2x minus 2 equals 0, x is 1. I guess was that obvious? You didn't need to get a slope of 0 at the, well, I mean, I guess you did because f prime of 1 from the left was equal to 0, so maybe you did. But anyway, I had to do that to be sure what was going on. I'm making a sign chart. Slightly confused sign chart. F prime 1. This is what happens when you do real AP questions. You have to like really think it through. All right, to the left of 1, we're supposed to use this definition, and we want to plug in something to the left of 1, so like negative a billion. That'll give us 2 plus like 2 billion, so very positive. We're definitely increasing there. To the right of 1, we use this definition. We plug in like a billion. Always, this thing's always increasing. What are we looking for? What intervals is f of x is increasing for all x? So, okay. So, I mean, what can we say? F prime of x greater than 0 for negative infinity to 1. And 1 to infinity. Therefore, f of x is increasing on negative infinity to infinity. All x. All right. A little weird, or at least different. Find all points of inflection of the graph. Support your conclusion. Okay, so I'm going to use this f prime to get f double prime. And then we're just looking for a sign change. How much space do I have? I have plenty of space. All right, f double prime is negative 2 when x is... Basically, when you find a derivative of piecewise, you drop the equality, and then you go back and maybe you can add it back in, assuming that like from the left and the right, you get the same value. That's what I always do. So here's 2, x is greater than 1. So, that says since f double prime changes negative. Actually, you know what? Just change its sign. Doesn't matter that it goes negative to positive. Change its sign at x equals 1. F of x has POI at x equals 1. Now, let me read the question again and make sure it wasn't like find the point. Find all points of inflection. It says points of inflection, so we have to plug it in, I guess. So what's f of x? F of x is this. If we plug in 1, we get 2 minus 1, which is 1. You should be able to plug it into either of them. You get 1 minus 2 is negative 1 plus 2 is 1. So point of inflection is 1, 1. POI is 1, 1. Make sure you answer the question. That's a big deal. Go back and answer questions. All right, let's see what number 5 has to say here. (1999) AB4. Suppose the function f has a continuous second derivative for all x, that f of 0 is 2, f prime of 0 is -3, f double prime of 0 is 0. Let g be a function whose derivative is given by g prime is e to the -2x, 3f of x plus 2f prime of x for all x. Okay, write the equation of the tangent line at 0. Tangent line to f. I don't know, this question feels unrelated to this unit, but it's going to be, what is f? So y minus 2 is f prime x minus 0. There we go, 3 points. Is there sufficient information to determine whether or not the graph of f has a point of inflection at x equals 0? Explain your answer. We know f prime is a point of inflection? We know f double prime is 0, but we do not know if there's a sign change, so I'm going to say no. No. F double prime of 0 is 0, but we don't know. My handwriting is not good. If there is a sign change in f double prime. If I had good handwriting, I would have written like, although we know that f double prime of 0 is 0. But no, there's not enough information. For a point of inflection, you need to have a sign change. Actually, you don't even need f double prime to equal 0. You just need f double prime to have a sign change. F double prime could not exist, and you could have that. Given that g of 0 is 4, equation of the tangent line, so g prime, oh god. Okay, so we need g prime of 0 is going to be, so I'm plugging into this, it's going to be e to the 0, 3f of 0 plus 2f prime of 0. So don't be afraid of these. They like give you the information, you just have to like use it. 3f of 0 you can see is 2. Nope, don't close that. Plus 2f prime of 0 is -3. So that's whatever that is. 3 times -4, so -12. And so our tangent line is, we know that, do we know something? We know g of 0 is 4, so it's going to be y minus 4 is the slope we got, x minus 0. Again, not really related, but whatever. Show that g double prime is this monster. Does g have a local max at x equals 0 and justify? So because we're finding g double prime and we're asked about a local max or min, I'm immediately thinking second derivative test. So we just have to find, oh man, we have to find the derivative of g prime. I'm going to copy g prime here and then move it down. G prime e to the -2x, 3f of x plus 2f prime of x. So a really important like AP thing about this problem is that even if you can't do it, if you cannot successfully show that g double prime is what they claim it is, you can still use what they gave you to answer the question. And that's like really important. So never give up, like answer whatever you can. G double prime. This is a product rule. So first, derivative of the second is going to be 3f prime 2f double prime plus second, which is 3f 2f prime, derivative of the first, which is -2 e to the -2x. All right, so we can take out this and like only that. So e to the -2x. So we have 3f prime, and then you're going to end up with -4f prime because of that. So 3 and -4. So I'm going to say -f prime of x. We're going to have 2f double prime and just 2f double prime. So plus 2f double prime. And what else? We got, whoa, what are you doing? This is -6 f of x. So then what was it supposed to equal? We get negative 6f of x minus f prime, 2f double prime, e to the negative x. Nailed it. Check. I don't know. Check. Did it. All right, now I'm going to find g prime of 0 unless it was given, which would be awesome. G prime of 0 is not given. We need to work it out. Okay, so g prime of 0, I'm hoping is just 0. Or actually, I'm kind of hoping it's not 0, because then definitely we know that it has neither max nor min. Did we do this? G prime of 0, oh, g prime, I got g prime of 0 is negative 12, which means there's no way there's a max or min there, which makes me feel like maybe I got g prime of 0 wrong. Not 0, therefore neither max nor min. Nor min at x equals 0. I feel like I might have gotten that wrong, because like it really feels like they would have set this up. F prime is negative 3. Okay, so I'm checking this, right? I'm plugging this in for this. So e to the 0 is 1. We got 3 times 2. And then, 3. We got 3 times 2. I messed up my parentheses. That's what happened. Hold on, we got to go back and fix this. 3 times 2. So it's kind of interesting that like, I mean, you're watching, right? Like, I messed up, and now I like know that I messed up because the next question seemed to suggest that we should be doing something else, which is good. So we get 3 times 2, and then 2 times negative 3. Yeah, this is supposed to be 0, which means this is 0, which means we actually get our tangent line is y equals 4. Okay, so now we got to change this up. So now we know that g prime of 0 is 0. G double prime of 0 is e to the 0 negative. I wish I could see these values better or something. Maybe I'll copy them. F of 0 is 2. F prime of 0, negative 3. F double prime of 0 is 0. Okay, let's bring these down here, just so we can like look at them while we plug in, right? So it's going to be negative f prime, so 3, 2 f double prime plus 0 minus 6f, so minus 12, which is negative 9, which is less than 0. Let me erase these, get out of the way. Okay, so since g prime of 0 is 0, g double prime of 0 is less than 0. If you have to, you can think about a picture. We got concave down, horizontal, relative max. G of x has a relative max. Ah, God, what? Relative max at x equals 0 by second derivative test. There we go. Okay, so I made an error halfway through. I corrected it. I don't know. If you didn't keep watching, you wouldn't know that I did that. But if you did keep watching, you would hear me saying this. So I don't really know what I'm saying. I think these answers are all good. All right, let's do number 6, which is 2001 AB4. H is a function defined for all x not 0. H of 4 is negative 3. This is h prime. All right, find all the values of x for which the graph of h has a horizontal tangent. So h prime equals 0. H prime of x equals 0. X is plus or minus root 2, right? Because just set this equal to 0, move the 2 over, square root it, plus or minus root 2. Determine whether h has a local max, min, neither at these values. Justify. Okay, so therefore, I guess, I don't know, horizontal tangent at x equals negative root 2, x equals root 2. All right, I'm gonna do a sign chart. Also, I'm gonna write this in factored form for the purposes here. I'm gonna write x minus root 2, x plus root 2, and then x. All right, when you make your sign chart, it's all the zeros and discontinuities of the first derivative, as well as any discontinuities of the function, because weird stuff can happen there. So all of that like combines to mean that we need to put plus and minus root 2 and 0 on this thing. So h prime, we got negative root 2, we got 0, we got root 2. We got a test, right? So if we take negative a billion, which is over here, plug it in, we're gonna get a negative, a negative, a negative, 3 negatives, make a negative. All right, and then because everything comes from a first degree factor, there's gonna be a sign change everywhere. So this will be plus, this will be minus, this will be plus. Some people don't like using that. I really like using that. You could plug in 1, for example, which would give us negative, positive, positive, which is negative overall, which is a big problem. Why am I getting that? Negative 1 is definitely on that interval. Negative, minus, it's positive, positive, it's negative. What the heck? Does negative a billion not give you negative? Negative a billion has to give you positive over negative. Negative 1, let's go back to this. 1 gives you negative. Why is this happening to me? 1 minus 2 is negative over negative, which is positive. So then what did I do wrong here? Negative, oh, negative, and positive. Great, I'm glad that took so much of the video. You could plug in 1 here, obviously get a negative, plug in a billion here, get a positive. It's just like frustrating when you make a weird little mistake. We all have that. All right, so h of x has relative minimum at x equals negative root 2 because h prime changes negative to positive there. And then h of x has relative max at it. Nope, relative min. Okay. At both of them. So let's change this up and say at both of them. And at x equals root 2. And let's change there to at those x values or coordinates. Okay, that's fine. On what intervals, if any, is h of x concave up? So I'm going to start with this. I'm going to rewrite it and say that h prime of x is x minus 2 over x, because then h double prime is easier to find. So I don't have to use the quotient rule. I can just power rule this. 1, and then that's negative 2x to the negative first is 2x to the negative second. Okay, so h double prime of x is, let's say, so this is 1 plus 2 over x squared. So we'll say it's x squared plus 2 over x. And we're looking for concave up, so we need to do a sign chart. And it'll be for h double prime. And the numerator has no zeros, so we're just going to go 0. And then if we test negative a billion here, we will get definitely a positive, a negative, so negative. but we're looking for concave up. If we plug a billion in, we get positive, positive, positive overall. So we can say that h of x, I don't know what that therefore is there for, but, oh, that was kind of funny. Is concave up for x greater than 0 because h double prime of x is greater than 0. There. Nice. Write an equation of the line tangent to h of x at x equals 4. So we know h of 4 is -3. I like to throw these in. And I mean, I got it wrong on the last one, so good for them. H prime, let's just do up here and I'll carry it down. H prime of 4 is 16 minus 2 is 14 over 4, so 7/2, or 14 over 4. You don't actually have to simplify that. I'm going to. So tangent line y plus 3 is 7/2 x minus 4. And then part D says, does the line tangent to the graph of h at x equals 4 lie above or below the graph for x greater than 4 and y? Okay, so our sign chart for this, we have this. Okay, greater than 4. We are concave up. So h double prime of x is greater than 0 for x greater than 0, but also greater than 4, which is the question. Therefore, h of x is concave up for x greater than 4. And the tangent, so concave up is like this. You can see concave up, no matter where you are, the tangent line is below. And tangent line is below the curve. So I think that's the answer. Does the tangent line is below the curve? Okay, there you go. Nice. That one was pretty straightforward. All right, now we're gonna hit a run of these types of questions. This is a really common idea. You'll encounter it on the free response, on multiple choice, all over the AP exam. You're given a graph of the first derivative and you're just asked stuff about it. So I've had to modify these to make them look a little more modern. In particular, on the new exam or the newest versions of the exam, they always tell you where the horizontal tangent lines are, so you don't have to like think about it. So I added this in, hopefully correctly. So let's see if we can answer this. For what values of x does the function have a relative maximum? Relative maximum, f prime has to go from positive to negative. Here and only here. So our answer will be A, f of x has relative maximum at x equals -2. And our reason is because f prime changes positive to negative there. And that's it. Moving on. B. For what values of x is the graph of f concave up? Justify your answer. So concave up would be where f prime is increasing, right? Because if f prime is increasing, f double prime is positive, which means f of x is concave up on -1 to 1 and 2 to 3 because f prime of x is increasing there. Now, if you look it up, the actual question has more parts, but since we're just doing up to unit 5 here, those parts kind of exceed that. So I've kind of like cherry picked the parts that we're going to be doing from some of the questions. I think that's okay, and I'm sure you understand why, because if you're doing this when you're learning it, you just don't know the math yet. So that's it for that question. Now you notice this question, 1989 AB5, almost the exact same thing, or at least the same setup, right? We have the graph of f prime, the domain, and I again have added in these horizontal tangent line things because we need it. And also, I don't feel like it's super obvious. I mean, like in here somewhere, here maybe more obvious, here maybe more obvious. This one not as clear. All right, so for what value of x does the graph of f have a horizontal tangent? So we're looking at f prime. Horizontal tangents are just going to be where we have zeros for this thing. Here, 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 here. Lots of them. We don't need to justify it, but also maybe I shouldn't circle the number so I can actually like see it. I mean, I think we know where they are, but still. So A, f of x has horizontal tangent at x equals -7, -1, 4, and x equals 8. And let's give a reason. We'll say because f prime of x equals 0 there. And that's it. You just got to get good at reading the graph, right? Relative maximum would be where we go from increase, well, a relative max is when f goes from increasing to decreasing, which means f prime goes from positive to negative. So that would be here and here. So let's answer f of x has relative maximum at x equals -1 and x equals 8. And our reason is because f prime changes positive to negative there. So this sounds like weird advice, but you do not want to have to think about what your justification will be. All you want to think about is where is it happening so you can then write the justification. So like for me, seeing a graph of f prime, I immediately think if they ask me about a max or a min, I'm going to be saying it's either because f prime goes positive to negative or negative to positive. The only question I have is where does that happen? And that's what you want to do. You need that like confidence going into it. All right, for what values of x is the graph concave down? So concave down would be where f prime is decreasing, which will make f double prime negative. So here and here. All right, so that looks like -3 to 2. So f of x is concave down on -3 to 2 and 6 to 10. 6 to 10. And our reason, because f double prime, nope, f prime. So we have the graph of f prime. Everything should be based on this. So f prime of x is decreasing there. And if you don't like just that, which is totally acceptable, you should say f prime is decreasing, which kind of implies that f double prime is negative. That would be okay. But you really want to mention what's going on with f prime so that it like makes sense to people. All right, so let's look at another one of these. These might be my favorite type because I think they're super straightforward. All right, the figure, this is just f prime again. Same deal. Relative maximum. Relative max, I'm going to highlight this time. So we need f prime to go positive to negative. This is the only place that is happening. So we will say f has relative max. God. So I have dyslexia, which impacts my reading. It also impacts my writing sometimes. Like I don't know what my hand is even doing while my brain is like telling me what to do. So relative max at x equals -2 because f prime changes positive to negative. There you go. Okay. For what values relative minimum? Okay, I guess we're hitting all of them. That would be where f prime goes negative to positive. So here, so we will say f has relative minimum at x equals 4 because f prime changes negative to positive. There. Okay. On what intervals is the graph of f concave up? Use f prime to justify. I like that they said that. They don't say that anymore usually. Like you have to just know what to do. So concave up would mean that f prime is increasing, because if f prime is increasing, f double prime is positive, and if f double prime is positive, you're concave up, all that stuff. So concave up, f prime increasing here and here. So we just need to write those down. So f is concave up on -1 to 1 and 3 to whatever that is, 5. And we'll say because f prime is increasing there, or on those intervals, whatever you want. My handwriting is bad, and I don't like to overwrite if I can avoid it, so I would go with that. All right. Look at another one. I think this is the last one of this type that I pulled out. There's more of them. If you go searching, you will find a lot of examples of this. This is one of the ways that they definitely hit Unit 5, I guess. Figure above is graph f prime, the derivative, same setup. Find all x attains relative minimum. Relative minimum is f prime going from negative to positive. That's happening here and only there. So our answer to A, f of x has relative minimum at x equals -1, because f prime changes negative to positive. There. Blah. That says there, believe it or not. There. T-H-E-R-E. Okay. Find all values of x, relative maximum. So relative maximum is f prime going positive to negative. So we have this. So positive, I mean, like this point is the one that they like want you to choose for something, but that's a bounce, right? There's no sign change in f prime rather. So that's not going to be an answer for a max or a min. It will be a point of inflection if we're asked about that, which we're not for some weird reason. Newer tests, they ask about points of inflection more often in my experience, but I kind of restricted myself to old things here. So f of x has relative max, that's weird, at x equals -5, because f prime changes positive to negative. There. T-H-E-R-E. It's like, slow down, brain. What are you doing? Okay. Find all values of x at which f double prime is less than 0. I wonder, like, why did we haven't had to use well, I don't know what I'm pointing at here. The vertical tangent line at x equals 3. So like f prime changes concavity there? Is that what they want us to say? I mean, but it didn't ask about that. I don't know. Oh, maybe there's more. There might be another part that maybe I cut out. I don't think so, though. Anyway, f double prime less than 0 would be when f is decreasing. So f is decreasing here. Oh, sorry. F prime is decreasing, right? If f prime is decreasing, f double prime is negative. So there, and then also here. So, I mean, I think those are the answers. All right, so f double prime is less than 0. I guess f double prime doesn't exist at x equals 3. Let's use that. Let's address that, right? F double prime doesn't exist because if f prime has a vertical tangent at that value, right? Vertical tangent. So like like this, that means that the derivative of this graph will not exist there. So I'm going to break up my interval. I bet that's like a secret point that a lot of people lost. First, let's say less than 0, 4. We got -7 to -3. -7 to -3, comma. We're going to go 2 to 3. 2 to 3. And then we'll say 3 to 5. 3 to 5. And our reason is because f prime is decreasing on those intervals. And then like I'm going to address it. I'm going to say f double prime of 3 does not exist. All right, I think that's good. All right, on to number 11, which is 1981 BC 7. There are not 7 questions on the exam anymore. There's only 6 free response questions, but there used to be 7. BC 7 part A. I don't really know what this would fall under, but I kind of wanted to do it, so I threw it in here. F is a differentiable function with f of 1 equals 1, and d dx of f of 2x equals f prime of x for all x. Find f prime of 2. I don't know, I just thought it looked neat. So d dx of f of 2x is going to be f prime of 2x times 2. So what do we know? So f prime of 2x times 2 is equal to f prime of x. And we want f prime of 2. So I'm going to plug in 1, because if I plug in 1, I will get f prime of 2 times 2 equals f prime of 1. Okay, so f prime of 2 times 2 equals f prime of 1. It's like at x equals 1. So f prime of 2 is 1/2 f prime of 1. And f prime of 1 is given, it's 1. So f prime of 2 is 1/2. And that's it. I just liked the question, and that's why I included it. So number 12. All right, this is 1982 AB2, and we're only doing part C. Find the vertical and horizontal asymptotes of f of x shown above. So what I'm going to do is I'm going to start with factoring. So f of x is x squared minus 1, which I'll make x plus 1, x minus 1, over x squared minus 4, which will make x plus 2, x minus 2. Okay, so we have a removable discontinuity at x equals 0 because we can literally remove it, right? It shows up in both. So we'll do x plus 1, x minus 1 over x plus 2, x minus 2. And this will be true when x is not 0 because we have a removable discontinuity there. Vertical asymptote is when the denominator is 0 and the numerator is not. So we'll have that at x equals -2 and x equals 2. Horizontal asymptotes are limits to infinity. Limit as x approaches infinity of f of x. I'm going to go back to the original instead of the factored form because I think it's easier to deal with. X cubed minus x over x cubed minus 4x. So you can look at this and see that the answer is going to be 1. One option is divide everything you see by x cubed. So what I'm really going to do is I'm going to like multiply by 1 over x cubed over 1 over x cubed, which gives me the limit as x approaches infinity of 1 minus 1 over x squared over 1 minus 4 over x squared. And if x goes to infinity, the 1 overs just kind of disappear. So we get 1. So therefore, y equals 1 is horizontal asymptote. Since this is a rational function, the limit to infinity and negative infinity, if it is a finite value, will always be the same. So we don't need to go to negative infinity on this one, but only because this is a rational function. All right, not bad. Let's go on to number 12. Let's go on to number 13. Did I number them wrong or did I just say it wrong? I said it wrong. All right, 13. Let f be defined by f of x equals the quantity x squared plus 1 times e to the negative x between negative 5 and 5. For what value of x does f reach its absolute maximum and justify? And then we want points of inflection. All right, so we're going to need f prime. F prime of x is first. Derivative of the second is negative e to the negative x plus second. Derivative of the first is 2x, which is e to the negative x squared minus 1 plus 2x, which is e to the negative x. Kind of forgot what I'm doing here. Negative x squared plus 2x minus 1. I don't like it, so I'm going to take out a negative. Negative e to the negative x squared minus 2x plus 1. And let's factor that. So f prime of x is negative e to the negative x, quantity, x minus 1 squared. Okay, so what do we want to do? It's absolute maximum. So I'm getting that the only critical point is 1. So f prime of x equals 0. X is 1. There's not going to be a sign change there. So, I mean, are we getting that we're getting that the maximum is going to be an endpoint? Doesn't really make sense to me. So did I get the derivative wrong? Let's see. First, derivative of the second, definitely. Plus second, derivative of the first, definitely. So you got e to the negative x. So that left me with negative x squared minus 1, 2x, good. Negative x squared plus 2x minus 1, good. Took out a negative. X squared minus 2x plus 1, good. Which is this? Okay, so I think it's just happening. Let's see. Negative 5. 5. So no matter what I plug in here, I'm getting a positive. And no matter what I plug in here, I'm getting a negative. So this is just always negative. So you're decreasing everywhere, which must mean that the absolute maximum is at the left endpoint. And the absolute minimum is at the right endpoint. So I guess one option here is to say f of x is decreasing on negative 5 to 5 because f prime of x is less than or equal to 0 there. Therefore, absolute max is at x equals negative 5. So decreasing everywhere, it doesn't matter what it looks like. It would be something like this. Like you have to get your absolute maximum at the left endpoint if you're always decreasing. So are we looking for the x coordinate? Yeah, so I mean, this would be my answer. Another thing I could do is I could candidates test this, where I do x and then f of x, and I do negative 5, 1, and 5. Am I going to be able to figure this out, though? Maybe. This will be 26 e to the 5th. This will be 2e to the negative 1st, and this will be 26 e to the negative 5th. And I mean, this is like by far the biggest value. So another option is to say that the absolute maximum must occur at an endpoint or a critical point, and therefore the absolute max is at -5. So that's right, even though it just did not feel right. But okay. Find the x-coordinate of all points of inflection. We're going to need f double prime. F double prime. So I don't know. I think it's a little weird that I'm making this video on Christmas Day, but I think it's really weird that my neighbor is out chainsawing on Christmas Day. So, you know, to each their own, I suppose. But if you're hearing chainsawing, that's what that is. Negative e to the negative x. X minus 1 squared. All right, f double prime. First, derivative of the second, 2x minus 1 plus second, derivative of the first. So the negative goes away because of the chain rule. We really have negative e to the negative x times -1. We're going to take out... So sometimes I just do equals and sometimes I write f double prime or whatever again. I don't think it really matters, but I am not consistent with it. So let's say this is -2x plus 1. And then x squared. You know, I could take out, and I should, let's take out an x minus 1 as well. Just to make life easier. We'll get -2 plus x minus 1. That actually, I think that makes life a lot easier. Okay, so I have e to the negative x. X minus 1. X minus 3. So if we're looking for points of inflection, it's going to be at 1 and 3, but I'm going to sign chart that. And then say f double prime has a sign change. So here it goes. I guess technically -5, 1, 3, 5, but like -5 and 5 are arbitrary. Like they're just a part of the problem. There's nothing about the function that says you need those, which means like we can still test like -1 billion because nothing interesting is happening. But this is always positive. So really we just get a quadratic that opens up. Like you get this. So we're definitely going to go plus, minus, plus. The key thing though is the sign change. Plus, minus, plus. Okay, so f of x has point of inflection at x equals 1 and x equals 3. And our reason is because f double prime has sign change. And I'm just going to write there. Should be like at those values would probably be better, but that's what I'm going to go with. All right. Next up. Find the x-coordinates. Okay, this is 1973 AB5 part A. Absolute maximum point for the curve y equals x e to the negative kx, where k is a fixed positive number, and try to justify. All right. Absolute maximum would occur at an endpoint, but there are no endpoints. So my hope is that I just have like, I don't know, something that goes like, probably it's going to go like this or something, I don't know, like a maximum. So let's find the derivative. Let's call it y prime. Y prime is, first, the derivative of the second is e to the negative kx times negative k, plus second to e to the negative kx, derivative of the first, which is, you can take out e to the negative kx, and then you will have x, nope, negative kx, negative kx plus 1. Okay, so if y prime equals 0, that means that x is 1 over k. And k is positive, which means that this is greater than 0, which is, I don't know, probably relevant. I'm going to make a sign chart. So we only have one critical point. So this is good because if this is a relative maximum, it will be the absolute maximum. Now, how do we check this? Well, this is definitely greater than 0, right? Because k is a fixed positive, positive number. So this is greater than 0. So if I plug in like negative something, this is always positive. And then I'll have, if I plug in negative, I'll have a negative and a negative, which is positive. So this is positive. So positive, positive. Okay, so we are positive here, and this is y prime. And then if I plug in like, I don't know, a billion or something, definitely negative, definitely positive, so negative overall. All right, so our reasoning will be y has relative max at x equals 1 over k because y prime changes positive to negative there. Okay, so that's good. And then I'm going to say since x equals 1 over k is the only critical point, y has absolute max there, right? It's not possible for it to get any higher than where it is here, because to get higher, you know, say this is 1 over k and you get higher, you'd have to have another critical point that happens here so that you could turn around and go back up. So the logic is really sound. I use this as my justification frequently. We want the coordinates though. So the coordinates of absolute max are 1 over k, comma, if I plug 1 over k in, I get 1 over k e to the negative first. That's interesting. There we go. Okay. Not bad. Let's take a look at the next one. (1976) AB 5. It says part A, but this pretty clearly says part C, so I'm not sure which it is. Hopefully it's one of them. All right, given the function defined by y equals e to the sine of x for all x such that negative pi to 2 pi, find the x and y coordinates of all maximum and minimum points on the given interval, justify your answer. So I don't know if I need to distinguish them or if I can just like find them, but let's start off with the derivative because that would be how we find maximums and minimums. So y prime e to the sine of x times the derivative of sine, which is cosine. Y prime equals 0. So e to the sine of x is never 0, so you don't need to worry about it. So really this just means, this just means that cosine of x is 0. Now think about cosine, or graph cosine, which is actually what I'm going to graph cosine on the interval from negative pi to 2 pi. That's probably a smart move. So negative pi to 2 pi. I'm actually going to graph it from negative 2 pi to 2 pi because, I don't know, that's how I usually graph cosine. So 2 pi, pi, tick, tick, negative 2 pi, negative pi, tick, tick. So we'll go here, 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 here. So what's helpful about this is that it's also our sine chart, right? Like, we know that the e thing is always positive, so the only thing making y prime positive or negative is cosine. And so we can use this to say that there's going to be a relative, so this is cosine of x. It's cosine of x, but it's also the sine of y prime. So we're going to have relative minimums. I don't know what color to use. Relative, that's a maximum. Relative minimum here, and you're going to get a relative minimum here, and then you will get a relative maximum here. Okay, so is this the only thing we're doing? Yeah, all right, so y has relative minimum at x equals, so this is negative pi over 2, and this is 3 pi over 2. negative pi over 2, and x equals 3 pi over 2. And our reason will be because y prime, not f prime, changes negative to positive there. So then our coordinates are negative pi over 2, comma, I mean, they're kind of ridiculous, e to the sine of negative pi over 2. The sine of negative pi over 2 is negative 1, so e to the negative 1. And 3 pi over 2. And then the sine of 3 pi over 2 is also negative 1, because they're coterminal. So e to the negative 1. And then relative max at pi over 2. Y has relative max at x equals pi over 2. And our reason, because y prime changes positive to negative there. Coordinate. I guess this should be like coordinate, I don't know, graph coordinate or something. Like, I don't want people to think that it's the coordinate on the derivative, right? So graph coordinate is pi over 2, and then it's e to the sine of pi over 2. The sine of pi over 2 is 1, so e to the first. There you go. Okay, so now, should I have checked negative pi and, well, no. No. Because at 2, we get e to the, is this on a closed interval? Maximum and minimum points on the given interval. See, they don't mess with this anymore because they would give you like an open interval. So like, what are we getting there? We would have, at x equals negative pi, we would have negative pi e to the sine of negative pi is 0, which is negative pi 1. Okay, so that's not the minimum or the maximum. Okay, I was just confused for a second. But you know, when you're confused, you gotta like check, right? So like, all of a sudden I was just like, what if it happens at an endpoint? 2 pi is gonna give me e to the sine of 2 pi e to the 0. So yeah, 2 pi 1. Those are like in the middle. I don't know, for a second there I was like, oh my god, it's a closed interval. I should be using the candidates test. But we answered it. Here's my answer for sure. Next up, number 16. All right, so now we're going to start doing like some sort of applied maximum minimum problems as far as the AP exam is sort of concerned with that issue. I will say that this is definitely something that is, the traditional max min problems don't show up on the AP exam as much as they used to, which I don't know, some people like, some people don't like. Up to you how you feel about it. Let's try to answer this. Rectangle, this is 1980, AB2. ABCD, sides parallel to the coordinate axes, point C in quadrant 1, so this is point C, is inscribed in the graph of y equals 4 minus 4x squared. Find the x and y coordinates of C so that the area of ABCD is a maximum. So let's just list this point right here is x comma 4 minus 4x squared. Okay, so now think about what we're doing. We're going to do 2 of that x value and then times the y value. That's the area. And do we know what this is? Because this is like the maximum you could possibly have, which would also definitely give you an area of 0. And then I would say the minimum x you could have would be 0. So 4 minus 4x squared equals 0. So x is 1, right? So we're going to have to be between 0 and 1 to find our area. So the area of the triangle is 2x, right? Because that's this. And then times y, but y is this. So 2x, 4 minus 4x squared, a prime. Actually, let's write this as 8x minus 8x cubed for derivative purposes. So 8 minus 24x squared, a prime equals 0 gives us x squared is, subtract 8 divided by negative 24 is 1/3. So x is plus or minus 1 over root 3. But because we are restricting ourselves 0 to 1, we'll say x is 1 over root 3. Okay, so we can do, there's only one critical point on the interval from 0 to 1, so we can do the only critical point theorem, or we can do the candidates test. So I'm gonna do, maybe I'll do both. I'll just say a double prime is negative 48x. So a double prime of 1 over root 3 is less than 0. So since a prime of 1 over root 3 equals 0, a double prime of 1 over root 3 is less than 0, a has relative, so concave down like that, relative minimum at x equals 1 over root 3. And then since only critical point, that doesn't look like a 3 at all, is the only critical point on 0, 1. A of x has absolute maximum. Do you see how I wrote minimum? What is this garbage? Get out of there. This should say maximum. Maximum at x equals 1 over root 3. Okay. So that would make the coordinates, so point C is 1 over root 3 comma, we got to plug into this, so that'd be 4 minus 4/3. So 4 minus 4/3, 12 minus 4 is 8/3, so 8/3. Okay, an alternative approach would be to say, I'm going to do it all in this color, a of x is continuous, therefore absolute max max at end point or critical point. And then we make our table, which has x, a of x, and we have 0, 1 over root 3, and 1. And then because of a of x, if you plug in 1, you get 0. If you plug in 0, you get 0. And we know that if you plug in 1 over root 3, you get 8 over root 3. So we would have 0, 8/3, not 8 over root 3. And then 0, therefore absolute max is 8/3 at x equals 1 over root 3 by candidates test. You know, the absolute max is not that. The absolute max is if we plug into this. So let's fix that. If I plug into this, I get 8 over root 3 minus 8 over, root 3 cubed, which I'm just going to write in here. And that's positive, I suppose. So is this, let's move this Editing on an iPad. It's a different world. There we go. And then our, therefore, coordinates are 1 over root 3, comma, 8/3. So that 8 is garbage, and you should erase it. And I'm saying that if you're a student, don't hand in work that had that looking 8 on it. Okay, so I don't know. That's all my work for that. Not bad, maybe. Let's look at this one, number 17. This apparently is 1996 BC1 Part B. But then it says D. I don't know. Somehow I labeled all of them wrong. Consider the graph of the function h given by h of x is this. Let A be the area of the shaded rectangle shown. Okay, so this is like kind of a similar thing. Show that A of w has its maximum value when w is the x coordinate of the point of inflection of the graph. So we got to find the point of inflection of h of x. So h of x, e to the negative x squared, h prime of x is, let's say, negative 2x e to the negative x squared by the chain rule. H double prime of x, first, derivative of the second is negative 2x e to the negative x squared plus second is negative x squared, derivative of the first, negative 2. Okay, so this is, I'm just going to take out e to the negative x squared. I know I could take out more, but this gives me 4x squared minus 2. Okay, so h double prime equals 0 gives us what? X squared is 1/2. So x has to be in the first quadrant. So x is 1 over root 2. Okay, so then I need to show that there's a point of inflection, I guess. So let's write this as 2 e to the negative x squared. And then it'll be like 2x, what? Do I want to factor that? 2x squared minus 1. So do I do like root 2x plus 1, root 2x minus 1? Root 2x plus 1, root 2x minus 1. I guess I do. Okay, so I'm just going to say that h of x has POI at x equals 1 over root 2. And my reason, it's my reason, because h prime changes sign there. Okay, so this is my point of inflection. Now, I gotta find the maximum area of this and show that it occurs at w equals 1 over root 2, I guess. So what's the area of this? A of w is going to be w times e to the negative w squared. Don't they sort of have to have the same thing? Because, like, I don't know. All right, a of w. A prime. I mean, it's like, this is just half of what is this half of? This is like half of, well, not exactly half. It's basically this. So we're definitely going to get the same like value out of it. So first, derivative of the second, negative 2w e to the negative w squared. Second, e to the negative w squared, derivative of the first, which is, let's take out e to the negative w squared. Should we take out a negative? Sure. Let's make it more obvious that that's a minus sign. Because again, don't submit garbage work. 2w squared minus 1. A prime of w equals 0. Gives us w is like plus or minus 1 over root 2. So w is 1 over root 2. How are we showing that this is a maximum? So first of all, I think this is only from 0 to infinity. So let's do a sign chart. a prime 0, 1 over root 2, and forever. So if we plug in here, I don't know, 1 over a million. This will be negative. This will also be negative, so we got positive. And then if we plug in a billion, we're definitely getting negative. So A of W has max at W equals 1 over root 2, because A prime changes positive to negative there. Okay, then we need to just say, I don't know, therefore show that A of W has maximum value when W is the x coordinate of the point of inflection. Okay, so I guess we just say that. Therefore, A of W has maximum at POI of, what is it called? H of x? H, sure. Of H. All right. I don't know. Did I love that problem? Not really, but we finished it. There you go. All right, let's take a look at number 18 here. 1972 AB4. A man has 340 yards of fencing for enclosing 2 separate fields, one of which is to be a rectangle twice as long as it is wide. So twice as long as it is wide. I don't know. Probably close to that. The other is going to be a square. Okay. The square field must contain at least 100 yards squared. So that's going to be at least. So greater than or equal to that. And the rectangle must be at least 800 square yards. If x is the width of the rectangular field, this is x. And then we're told, so if this is x and it's supposed to be twice as long as it is wide, this has to be 2x. So you kind of want to start with a picture, I think. And then we're told that the area of this must be at least 800 yards. So that means that 2x squared is greater than or equal to 800, which means x squared is greater than or equal to 400, which means x is greater than or equal to 20. Okay. So we're looking for the maximum and minimum values of x. So I think that's a minimum. And then what else are we doing? So there's no like obvious connection between the square. I mean, there is an obvious connection because no matter what we do, 340 total yards. But I'm going to call this y. And then because we know that there's got to be at least 100 square yards for that, y squared has to be greater than or equal to 100. So y has to be greater than or equal to 10. All right, now what do we do? Well, we need something that connects y and x, and it's got to be this, right? So the perimeter of this guy is going to be, there's x, and then 2x and 2x. So that's 6x's. 6x plus, there's 4y for the perimeter of this, has to equal 340. Let's divide by 2. 3x plus 2y is 170. So then y is equal to negative 3/2 x plus 85, which is kind of gross. Okay, so now we have that y is greater than or equal to 10, and this is y. So that means that negative 3/2 x plus 85 is greater than or equal to 10, I guess. So negative 3/2 x greater than or equal to negative 75. We're going to multiply by 2, divide by negative 3, and since we're dividing by a negative, we flip the sign. So that's a negative 150 divided, so 50. So I think the answer to the first part, which is like an algebra 2 question maybe, is 20 to 50. Somewhere between 20 and 50 is the value of x. All right, now what is the greatest number of square yards that can be enclosed in the two fields? Justify your answer. All right, so now we got to do like area. So the area of this is definitely 2x squared, and this is y squared. So this is all A. B, area is going to be 2x squared plus y squared. Now we have too many variables, right? We have x's and y's, so we got to get rid of one of them. I propose we get rid of y because we already know this, right? So from this information, we know that a is 2x squared plus the quantity. I'm going to, well, I guess I'll do negative 3 halves x plus 85. I don't like leading coefficients that are negative. I have a bias against them. Derivative, a prime, will be 4x plus 2, negative 3 halves x plus 85 times the derivative of that, which is negative 3 halves. Should we simplify that? Maybe. So a prime is 4x. The 2's cancel, and then we have a negative 3 to distribute, so I'll say plus 9x minus 240, 255. So what I've done here is this and this canceled, and I distributed negative 3. So negative 3 times negative 3 times negative 3 halves. There's a, so I did it wrong. This gives me 9 halves. And then I distributed negative 3 to this, and I thought negative 240 and another negative 15 is negative 255. I feel like that's right. And then this is 8, 17 halves x minus 255. This is going to be gross, maybe? I don't know. We need a prime to equal 0, which means that x is going to be 255 times 2, which actually I should do because that's 510, and 510 is a multiple of 17. 510 over 17, which is 30, right? Because 3 times 17, 30. Okay, so that's our only critical point. We can use candidates test on this because we know that x has to be between 20 and 50. So I propose to do that because the area is, do I propose to do that? I might do the only critical point test. That seems easier. Let's find a double prime. So from here, we're going to do a double prime is 17 halves, which is greater than 0. Okay, so this is interesting. So a prime of 30 is 0. A double prime of 30 is greater than 0. So a has a relative minimum, which means that's not the answer because we're looking to maximize the area. What is the greatest number? All right, therefore, the absolute max is either at 20 or 50. So good grief. What's the best way to do this? I just don't want to plug in. A of, all right, I don't know. I'm gonna do them up here in yellow. A of 20 is, what am I using? I'm gonna use this. So a of 20 is 2 times 20 squared is 400. That's 800 plus 20 divided by 2 is 10 times negative 3 is negative 30 plus 85 is 55 squared. Fantastic. So 55 squared is like 50 plus 5 squared, which is going to be 2500 plus multiplying together is 250 times 2 is 500 plus 25, so 3025. So 3825, I hope. And then A of 50 is going to be 50 squared is 2,500 times 2 is 5,000. This feels like a good candidate for the biggest. 50 divided by 2 is 25 times negative 3 is negative 75 plus 85 is 10 squared is 100. So 50, 100. Okay. I'm going to copy these. 50? Yeah, I guess. I don't know. Did I get that wrong somehow? Those numbers feel a little off, but I'm going to live with them, I guess, and say, therefore, absolute max area is 5,100 when x is 50. Does that even answer the question? What is the greatest number of... Yeah. Okay. Do I really think that's right? I guess I do. I don't know. I mean, clearly I kind of don't. But I'm going to live with it. 25, negative 75, 10, 50. Yeah, I mean, I think it's right. I don't know. Look at me getting shook by some arithmetic. All right, number 19. A manufacturer finds it costs him... Notice they always male. There were no women existed on the AP exam until like probably the 2000s, to be honest. So they've become more aware of that. But a manufacturer finds it costs him x squared plus 5x plus $7 to produce x tons, which is I don't know if that's a typo on my part or if I just like went for it. At production, capital P, that's weird, levels above 3 tons, that must be, this is a typo. It's like, is this like some British thing? But I think that would have another N in it. He must hire additional workers, and his costs increase by 3 times x minus $3 on his total production. If the price he receives is 13 per ton, regardless of how much he manufactures, and if he has a plant capacity of 10 tons, what level of output maximizes profits? Okay, we're trying to maximize profits, and we need to write a function for profits. And I think it's going to be a piecewise function, like 0 to 3 and then 3 to 10. So I'm going to call it P of x. And it's going to have 2 branches. We're going to go 0 to 3 and then 3 to 10. So from 0 to 3, I'm going to say you make 13 times however much you make minus whatever it costs you. So minus x squared plus 5x plus 7. And that's going to be between 0 and 3. Okay, so then from 3 to 10, you still just make 13x minus, it's an additional cost, so you still have this, and then you just tack on more costs, I think. And that'll be from 3 to 10. We should clean that up. And then we're looking for the maximum. So P of x. All right, negative x squared plus 8x minus 7. So like you can help yourself out sometimes by doing a little bit of arithmetic. Negative x squared. What do we got in terms of x's? We got 13x minus 5x minus 3x. So 13x minus 8x is 5x. And then in terms of the constant, we have minus 7 and then minus negative 9. So minus 7 minus, what am I doing? Why am I not just writing it? Minus 7 plus 9 plus 2. I think that's right. Ooh, too many inclusions. And then there. Okay, do I really think that's right? I do. 3x minus 9 there plus 2. Yeah, I'm pretty pretty confident. Sure, why not? All right, P prime is negative 2x plus 8, negative 2x plus 5, 0 to 3. And then remember, we leave out 3 because it's where the branches come together, so we're not even sure if it's differentiable. And if you plug in 3, you get 2 here, and then you get negative 1 here. So it's not differentiable at 3, so we do not want to include that. 3 is a critical point. Potential critical points. P prime equals 0. Let's say on 0 to 3 would be x equals 4, which doesn't work. It's not on the interval. On 3 to 10, it's kind of an interesting problem because of the piecewise part. You would get x is 5 halves, which is 2.5, which is also not there. So the only critical point is x equals 3 because p prime of 3 does not exist. Okay, so that's our only critical point. I've lost track of what I'm even doing. What level output maximizes profit? So if we go from, if p prime changes positive to negative at 3, that'll be the answer. If not, it's either do nothing, like don't have a company, or make 10 tons, go for it. So sign chart, I suppose. Kind of feeling like the answer is definitely going to be 3, but we still have to check. So this is for p prime. Now, on 0 to 3, p prime, so we can plug in anything between 0 and 3. Like 1 is between 0 and 3, and it gives us a positive. And then between 3 and 10, so plug in any number between 3 and 10, like 8. 8 gives us a negative. Okay, so p of x has relative max at x equals 3 because p prime. I like this problem. Like it's a twist, I guess. Like you don't see this a lot. Positive to negative there. X equals 3 is only critical point. Use this more than you'd think. Therefore, p of x has absolute max at x equals 3. And then what are we trying to answer? If the price is this, what level of output maximizes the profits? Profit, I'm just going to write profits maximized. When x equals 3 tons. Okay, so when the output is 3 tons, I don't really know if I need to go that in depth with my description, but I'm not gonna. All right, number 20. A tank with a rectangular base and rectangular sides is to be open at the top, so no top on this thing. Should I try to draw that? Yes. I can, like, this will make a rectangle if I don't mess up. There we go. Whew. And then I can duplicate and like move it a little bit. Let's move it here. Then I can connect them. Dope. It's the little things. Yeah, I enjoy doing this. Taking advantage of the built-in shapes because I do not have a very, like that one should probably be dotted to be better, but whatever. The tank is to be constructed so that its width is 4 meters. Its width is 4 meters. I don't know. Okay, 4. Its volume is, what are we doing? Its volume is 36. Building the tank costs that. What does it cost? rectangular base, rectangular sides, open to the top. I'm calling this x. I'm calling this y. Okay, so I'm going to say that the volume is 36. So 4 times x times y is 36. If the building the tank costs $10 per square meter for the base, so it's $10 for the base, and the base is 4x. And $5 per square meter for the sides. So the sides, all right, we got 5. One side is 4y, right? 4 by y is the area, so 4y per square meter. Yeah, 4y. And there's 2 of those, so times 2, right? The front and the back. And then another one is xy, and there's 2 of those. So plus 5xy times 2. And this is our cost, so let's call it C. Okay, and our objective is to minimize the cost. So these questions always come down to like reading the problem, pulling off equations, and going from there. So like I always try to draw a picture if possible. I will try to get equations out of the problem and then just turn into a calculus problem. Like I don't want to keep thinking about the scenario. So at this point, C is equal to, we got 40x plus 20y, 40y, and then 5, 10 plus 10xy. Okay, so what do we know? This has too many variables, so our objective now is to get rid of one of the variables, and the way we do that is we use this relationship. So from here, we know that xy is 9, which means that y is 9 over x. So now there's an interesting thing here because xy is 9 and this is an xy. So I'm going to turn this into 90 using this, and then I'm going to change using this into that. Yeah, so C is 40x plus, okay, we're going here, right? So that's 40 times 9 is 360 over x. And then I'm going to use this to say plus 90. Now I'm going to go back to the same color, but just to like highlight what has happened here. We're trying to maximize this thing. Maximize, least expensive. We're trying to minimize this thing. C prime 40 minus 360 over x squared. Got to figure out what makes this 0, right? So C prime equals 0. Common denominator, 40x squared minus 360 over x squared is 0. Okay, so cross multiply. You're not really, math teachers, modern math teachers or something don't like cross multiplying, but that's what I've always called it. Like I'm gonna multiply both sides by x squared, whatever. Cross multiply, the denominator's gone. X squared is 360 goes over, divide by 40, which gives you 9. So x is plus or minus 3, but negatives don't make sense. So x is 3. So now our hope, since there is only one critical point, there's probably like some boundaries or something we should have here. I don't really think there are though, because like the relationship is xy. Like technically, I guess x could be like 1 over a billion, and then y could compensate for that, and you could still get 36. So maybe there are not implied bounds. Our hope is that this is a relative minimum so that we can say it's the only critical point, therefore absolute minimum. I'm going to use the second derivative test, and I'm going from here to here. So it's going to be negative 360, so we could think of this as negative 360 x to the negative second. So that'll be 720 over x cubed. It's really 720 x to the negative third, such that x equals 3. The relevant thing is that this is greater than 0. Okay, so since C prime of 3 is 0, and C double prime of 3 is greater than 0. C of x has relative minimum at x equals 3. Oop, I'm like right up against the edge. I just assume I have like an infinite scroll, which I do not. Be nice though. X equals 3 is the only critical point. Therefore, C of x has absolute minimum at x equals 3. And then the real question is that the answer, or do we have to do something? What is the cost of the least expensive tank? So now we got to find the cost of least expensive tank is C of 3, whatever that is, which equals, we go up here and we plug in 3. So that'll be, let's do it in yellow, I guess. So C of 3 is going to be 40 times 3, 120, 360 over 3, 120, and then 90. 240 plus 90, 330. I think 330 probably dollars. Period. All right. Good one, I think. All right, that was number 20. Okay, now we are moving on to number 21. All right, back to 1969, BC3. The mean value theorem guarantees this was a multiple choice question, I think, and I just like got rid of the multiple choice options, so it's not actually multiple choice, not actually free response. Unlike all the others, I think the next 3 are going to be from super old multiple choice. Mean value theorem guarantees the existence of a special point on the graph of y equals square root of x between 0, 0, and 4, 2. What are the coordinates of this point? Mean value theorem. If a function is continuous on the closed interval, differentiable on the open interval, then there exists a c such that f prime of c equals f of b minus f of a over b minus a. The slope of the tangent line equals the slope of the secant line. So basically in this case, we are trying to do f prime of, I'm going to just do x and then say that, well, it doesn't even say here. So f prime of x should be equal to f of 4 minus f of 0 over 4 minus 0. This is like a very straightforward mean value theorem. So we're allowed to do it because f of x is continuous on the closed interval from 0 to 4 and differentiable on the open interval from 0 to 4. That's what's required. And actually what's interesting is f of x here is not differentiable at 0, right? Because when we take the derivative, so we're going to get 1/2 x to the negative 1/2, that does not exist at 0. But that's not a problem because we only need to be differentiable on the open interval. So endpoints do not hurt us here. The square root of 4 is 2, and then the square root of 0 is 0 over 4. So we're just 1/2 x to the negative 1/2 is 1/2 multiplied by 2, x to the negative 1/2 is 1. Square both sides, I guess, whatever. Raise both sides. Technically, you're going to the negative second, but we just get x is 1. And if x is 1, then y is the square root of 1, which is 1. So our point is 1, 1. This problem is not a big deal, but it's important. Like, you have to be able to solve these types of problems. I'll show you how important it is when we look at number 22. Which is from the BC exam. It's number 13, and it's like essentially the exact same question. So f is the function given by x cubed minus 3x squared. What are all values of c that satisfy the conclusion of the mean value theorem of differential calculus? They don't say that anymore. They just say the mean value theorem on the closed interval from 0 to 3. So we need f of x is continuous. So I write this every time, not on a multiple choice problem, obviously, but also that doesn't look like anything. Continuous on the closed interval, differentiable on the open interval. So we're allowed to use the mean value theorem. All right, so f prime, so it should be f prime of c is equal to f of 3 minus f of 0 over 3 minus 0. So we have to plug in 3, we have to plug in 0. Plugging in 0 just gives 0. So f prime is going to be 3x squared minus 6x. So we're going to have 3c squared minus 6c, because we're doing f prime of c, is going to be, if we plug 3 in here, we get 27 minus 27. That's interesting. We get 0 minus 0 over 3. So we just get 3c squared minus 6c is 0. I don't know, take out 3c. C minus 2 is 0. So either c is 0 or c is 2. But now, the mean value theorem guarantees us, on the closed interval, 0 to 3? Applied on the closed. The mean value theorem should only guarantee us values on the open interval. So I think that the answer to this is 2. 0 happens to work, but was not guaranteed because it's not a part of the open interval. So I'm going to say there, I'll say MVT. This was multiple choice, by the way, so like you would just choose the answer and move on. Guarantees C is an element of the open interval 0, 3. Therefore, C equals 2 is the only value. I wonder if that's like the actual right answer from the exam. It should be. But, I mean, I could check, but I don't really want to. All right, next up. (1988) BC 24. I don't know why they were all on the BC exam. This, I assure you, also shows up on the AB exam in a similar fashion. So if C is the number that satisfies the what? How did spell check not get that? Of the mean value theorem for this, which is that the same exact function? X cubed minus 2x, no, super close. X cubed minus 2x squared on the interval 0 to 2, then what is C? All right, let's do it again. F of x is continuous on the closed interval 0 to 2. Differentiable on the open interval 0 to 2. Therefore, by MVT, f prime of c equals f of 2 minus f of 0. This is like free response style. For some c, it's an element of 0, 2. Okay, so that's free response. You would write this, and then you would just solve it. So that's what I'm going to do. F prime of x is 3x squared minus 4x. F of 2 minus f of 0. Just demonstrate in different work. I hope this doesn't end up 0 again. Actually, I kind of do. It does. What the heck? This is like the exact same question. 8 minus 8 over 2 is 0. So 3x squared minus 4x equals 0. Let's say therefore. Take out x. 3x minus 4 is 0. So either x is 0, which we're throwing out, or x is 4/3. So x is 0 is a coincidence. Like, it doesn't need to happen. It can happen. The mean value theorem doesn't guarantee that anything could happen there. So I'm going to say, therefore, C is 4/3. That's it. So these were straightforward. I chose these because I thought you should see that you will see straight applications of the mean value theorem occasionally on the multiple choice. More often than not, this shows up on free response questions, and there is a little weirder. So here's number 24. for example. It's 2009, Form B, AB3, Part C. So the graph of f, continuous function f is defined on the closed interval. The graph of f consists of a line segment and a curve that is tangent to the x-axis at 3, as shown in the figure. On the interval from 0 to 6, the function is twice differentiable with f double prime greater than 0. Okay. Part C said, is there a value of a between -4 and 6? So that's like anywhere on the entire interval. For which the mean value theorem applied on the interval from a to 6 guarantees a value of c at which f prime of c is 1/3. All right, here is my recommendation. We don't know what a is, but we do know that this interval should end at 6. If we look at the graph, we're at 6, 1. So what I'm going to do is from here, I'm going to draw a line that has this slope, right? Because mean value theorem basically says slope of the secant equals slope of the tangent. I'm going to take advantage of the slope of the secant idea. So slope of 1/3 starting here. So that'll look like, I gotta go 1, 3. We're actually gonna go through here. And then like, I don't know, keep going. So the answer is definitely yes. There is a value of a. The value of a is 3. Now, how do we justify this? I guess we'll first say yes. So, I mean, I think it's kind of they're trying to trick you because like on -4 to 6, the function is not differentiable at 0. It's got a sharp turn. Doesn't matter. We can find a. So I'm going to say yes, a is equal to 3. So let's do that. Yes, a equals 3. F of x is differentiable. Well, definitely continuous. Continuous on 3 to 6 and differentiable on 3 to 6. So continuous closed, differentiable open, f prime of c, so therefore by MVT, f prime of c equals f of 6 minus f of 3. 6 minus 3 equals 1/3 for some c element of 3, 6. I think that's it. Like, don't overthink it, but make sure you answer the question, right? So here, I've added in this extra purple line, which for me, like, basically answered the question. So don't be afraid to add lines. They can be really helpful. Let's look at another one. 25. Let g be a continuous function. This was 2008. Let g be a continuous function with g of 2 equals 5. The graph of the piecewise linear function g prime, the derivative of g is shown above, for -3 to 7. Find the average rate of change. Average rate of change is algebra 1 slope, so of g prime. So first, we're going to do g prime of 7 minus g prime of -3. 7 minus -3 is, okay, 7 gives us 1. -3 gives us -4 over 10 equals 5 over 10. 1/2 is average rate of change. Okay, so, and it's also the slope of the secant. Like, it doesn't matter that this thing is like a differentiable nightmare. That's still the slope of the secant line between those points. Does the mean value theorem applied on the interval -3 to 7 guarantee a value of c such that g double prime is equal to this average rate of change? Why or why not? So as I said, this is a differentiable nightmare. There are multiple places. Not differentiable, not differentiable, not differentiable. The answer is no. There is no value guaranteed. And actually, does it happen? Oh, it does happen, but that does not matter. So the answer is, since, oh boy, since, it's like my writing is bad and it's kind of worse on the iPad. Since g prime is not differentiable at, I'm going to list all of them. You only need one. X equals -1, 1, and 4. X equals -1, X equals 1, and X equals 4. And then in parentheses, I'm going to say G prime has sharp turns. Sharp turns at those values. Okay, since that is true, MVT does not apply on -3 to 7. Okay, so they're trying to trick you. Yeah, I don't think I ever in my life noticed that they were trying to trick you because I just look at it and I'm like, not differentiable, so mean value theorem does not apply. I mean, technically the slope is 1/2 here, which is kind of an interesting lesson because the mean value theorem guarantees that something happens. If the conditions of the mean value theorem are not satisfied, it doesn't mean that it cannot happen. It just means that it is not guaranteed to happen. So the mean value theorem does not guarantee anything in this case. So that would be my answer. All right, should we look at another one? I forgot to put in the letters on this one, but this is 2007 AB3. The functions G, so this is A and B, I'm pretty sure. A and B. Explain why they're, okay, well, f and g are differentiable, g is strictly increasing. The table above gives values of the functions and their first derivatives at selected values. Function h is given by h of x is f of g of x minus 6. A, explain why there must be a value of r between 1 and 3 such that h of r is -5. So if you are given h and asked about h, it's almost always going to be intermediate value theorem. So like if you stay on the same level as the function, you're going to be using IVT most of the time. If you're down one level, so if you are given h and asked about h prime, it's almost always going to be MVT. So for A, I'm thinking this is an IVT problem, which means I need h of x to be continuous. So here's a fact that you are just going to state. You do not need to prove it. It is true. H of x is differentiable because a composition of continuous functions, of differentiable functions is differentiable. I don't know, why am I writing this up here? And differentiable implies continuous. So I really should have written that like for A. So there, that's A. That's how I would start A. I would say h of x is differentiable because a composition of differentiable functions is differentiable, and differentiable implies continuous. Now I'm going to try to find h of 3. So h of 3, well, I need h of 1 and h of 3. So let's find h of 1 first. H of 1 is f of g of 1 minus 6, which is f of g of 1 is 2, minus 6. F of 2 is 9, 9 minus 6 is 3. H of 3, f of g of 3 minus 6. G of 3 is 4, so that's f of 4 minus 6. F of 4 is -1, -1 minus 6, -7. Okay, so we have a continuous function. We have h of 3 is less than -5 is less than h of 1. Therefore, by IVT, which you can abbreviate, h of r equals -5 for some r that's an element of 1, 3. So IVT proves it. I think it is essential, though, that you establish that h is continuous because you can't use IVT if a function is not continuous. So make sure that you're nailing all of those parts. So I think we should start with that. All right, B, explain why there must be a value of C between 1 and 3 such that h prime of C is -5. All right, so we have said that h of x is differentiable because a composition of differentiable functions is differentiable. And we know that h is continuous because differentiability implies continuity. So I don't know. I'm gonna like copy this just so I have like a better looking answer. Let's see, duplicate. All right, so I would start my answer to B with this also, except I think if you've already established it in A, you can kind of just roll with it. Let's make this look better. Things you cannot do when you're writing on paper. Okay, there. So now what's convenient for us is that we found these values, that h of 1 is 3 and h of 3 is -7. I would say they made us put all the effort into that. We're going to use them more than once. So here I'll say, therefore, by mean value theorem, h prime of C is h of 3 minus h of 1. So if this didn't work, I would go back to the table and like try to find a place where this does work. But this is going to be -7 minus 3 over 2, -5 for some C that's an element of 1, 3. So mean value theorem to the rescue, right? So if you're staying on the same level, we're given h, we're asked about h, IVT. If you're going down a level, given h, asked about h prime, almost always MVT. If you walk in knowing that, it's like comforting, right? Because you kind of like already know how to attack a problem before it's even like stated. Okay, it looks like we are on number 27 now. This is 2007 Form B, AB6. You can see that I forgot to label them, so I labeled them A and B, but I'm not entirely sure that they're actually parts A and B. Let f be a twice differentiable function such that f of 2 equals 5 and f of 5 equals 2. Let g be the function given by g of x is f of x. A, maybe. Explain why there must be a value of C between 2 and 5 such that f prime of C is -1. Okay, so this is about f. We will say that f is differentiable. I don't have a pen. Here we go. A. F of x is differentiable, which implies f of x is continuous. All right, therefore by mean value theorem. So it's like, I'm not even really thinking about this. I just know that if I'm given information about f and I'm asked about f prime, it's going to be mean value theorem. And we were only told 2 points, so we kind of have to assume that this is going to work. By mean value theorem, f prime of C is f of 5 minus, I hate the way these points are like just kind of the same point flipped around. I feel like that's a mean thing to do to dyslexics such as myself, but that's all right. 2 minus 5 over 3, which is -3 over 3, which is -1, for some C that's an element of 2 to 5. Boom. All right, that's it. It's pretty straightforward. You still run into problems like that frequently. All right, B. Show that g prime of 2 equals g prime of 5. Okay, so g of x is f of x. So we're going to have to find g prime. This is a chain rule problem. So let's say here, g prime of x is f prime of f of x times f prime of x. All right, so g prime of 2 will be f prime of f of 2 times f prime of 2. I don't actually know what f prime of 2 is. Do I know what f prime of 2 is? I don't know what f prime of 2 is, so what am I trying to show? I'm just trying to show that g prime of 2 equals g prime of 5, so I don't really need to know the value, so that's good. So f of 2 is 5, and then f of 5 will be 2, so I assume we'll need to do that on the next part. So let's see, this will be f prime of 5, f prime of 2. All right, g prime of 5 is f prime of 5 times f prime of 5. And we said that f of 5 is 2, so this is f prime of 2, f prime of 5. Therefore, g prime of 2 is the same as g prime of 5. Okay, good. There's more to this, though. Use this result to explain why there must be a value of k between 2 and 5 such that g double prime of k is equal to 0. So this, I think, this is actually mean value theorem again, which is sort of unusual. But I think we're okay, because we're going to say that g prime is differentiable because g prime is a product of a composition of different, I'm just going to say it. It needs to be true. So g of x is differentiable for sure because it's a composition of differentiable functions. G prime, so f is twice differentiable, which means f prime is differentiable. This is a composition of differentiable functions. This is a product of differentiable functions. So this is definitely differentiable. So I'm going to say that g prime is differentiable and hope that I don't really need to justify it. So here goes. G prime is differentiable. Okay, so it's a product of, that's not an abbreviation. I don't know why I put a period there. Product of composition of differentiable functions and a differentiable function. I don't think you really need to justify this, but if you do, that's the reason that it is. Therefore, g prime is continuous. Okay, so we're going to use mean value theorem. Therefore, by MVT. And we're going to use the mean value theorem from 2 to 5 because we know g prime of 2 equals g prime of 5. So if we subtract them, we get 0. So by MVT, g double prime of k will be g prime of 5 minus g prime of 2 over 5 minus 2, which is 0 for some k that's an element of 2 to 5. So this is like, I mean, this is kind of an advanced way of doing it, but this is what mean value theorem will look like usually on the free response questions. So you get, you're given some information. Well, nope, that's not it. You're given some information and then you apply the mean value theorem. You frequently have to like establish differentiability, establish continuity, and then dive in with the conclusions. Let's take a look at another one. So 28, this is 2006, form B, AB6, and it looks like we're doing part D. Car travels on a straight track during the time interval 0 to 60. The car's velocity v measured in feet per second, acceleration a measured in feet per second, which is my preferred way of writing that. I know that physics will tell you feet per second squared. It's way harder to interpret that. Are continuous functions. The table above shows selected values. For this, must there be a time when a of t equals 0? So they're continuous. So since a of t is continuous, that means that v of t is differentiable, right? Because a of t is v prime of t, a of t exists everywhere, which means v prime of t exists everywhere. So v of t is a differentiable function. So a of t equals 0. Here and here we get the same value, so we can use mean value theorem on this interval, and that'll do it for us. So let's do that. Okay, so D. All right, what am I gonna say? I'm gonna say that A of t equals v prime of t is continuous. Therefore, v prime of t exists for all t in 0 to 60. Therefore, v of t is differentiable. Okay, which implies continuous, but also it was given that it's continuous. So, all right, we are going to go from here to here because they're the same value. I recommend you always look through the table. If you're trying to show 0, where something equals 0, look for the same y value because it just makes your life easier. So, therefore, by mean value theorem, v prime of t equals v of 25 minus v of 0 over 25 minus 0, which equals 0 for some t that's an element of 0 to 25, which therefore between 0 and 60 also, but I'm not going to overdo that. For some t between there, well, actually, maybe then I'll, therefore, a of t equals 0 for some t between 0 and 60. So I will overdo it. There we go. I just worry. I'm always going for like 100% on the exam, not just a 5. So I give, my explanations sometimes go a little over the top. This is another application of mean value theorem. Number 29. And this probably looked similar, maybe. This is 2005 AB3, metal wire of length 8 centimeters heated on one end. The table above gives selected values of the temperature in degrees Celsius of the wire, x centimeters from the heated end. Turns out you don't really need to understand that to do this problem, I think. The function t is decreasing, twice differentiable. Okay. Are the data in the table consistent with the assertion that t double prime is greater than 0 for every x in the interval 0 to 8? I wish I had formatted that differently. Explain your answer. So, I don't know. I'm going to try to find a place where t double prime has to be less than 0, I guess. So what happens? We go -7. Maybe I'll like fill these in. So this would give us -7, right? If we did the mean value theorem on that. This would give us -23 over 4. Okay. This would give us -8. Okay, so if, I mean, remember, we're faking our way through the mean value theorem right now, and then we're going to write it up. But mean value theorem guarantees that t prime is -7, and then that t prime is -8. If you go from -7 to -8, you must decrease, which means the mean value theorem applied to t prime will guarantee a t double prime value that is negative. So that's what I'm going to do. All right, so how am I writing this up? So t of x is differentiable, right? That was given, I think. Yes. Which implies continuous. Therefore, by mean value theorem, I'm doing it twice. So I'm going to say t prime of c1 is t of 1 minus t of 0. 1 minus 0 is -7 for some t1, nope, c1. C1 element of 0, 1. Semicolon. T prime of C2 is, we're going 5 to 6. So t of 6 minus t of 5. 6 minus 5 is -8 for some C2, which is an element of 5 to 6. Okay, so t is twice differentiable, which means that t prime is differentiable. T is twice differentiable. Therefore, t prime is differentiable, which implies continuous. You just keep walking through the criteria, right? Like to use the mean value theorem, we need continuous closed, differentiable, open. But if we're differentiable, we're definitely continuous. So differentiable is better than continuous. But anyway, therefore, by mean value theorem, t double prime of, I don't know, x, let's just say, is t prime of C2 minus t prime of C1 over C2 minus C1. Now this is definitely negative because I'm gonna move it a little so I can like fit stuff. This is definitely, maybe I'll move the whole thing. Okay, so this is definitely negative because C2 is bigger than C1 because C2 is from 5 to 6, whereas C1 is from 0 to 1. So the denominator is definitely positive. The numerator is -8 minus -7, C2 minus C1, -1 over C2 minus C1, which is less than 0. Therefore, t double prime of x is not always positive. On the interval, I don't know what the question was. On 0 to 8, right? So there, for every x, there's at least one x. So for all x, element of 0 to 8. There you go. There's at least one x we've proved for which t double prime is less than 0. So false or whatever. All right, that was a good one. And this, I think, is going to be the last one that we do. It's like the same question, which is what I'm trying to hammer home. Like, you just end up doing the same things over and over. It is worth going back to old exams to study. Like, I'm a huge proponent of that. Blood vessel, this is 2003 AB3 Form B. Blood vessel is 360 millimeters long, circular cross-section of varying diameter. Table above gives the measurements of the diameter of the blood vessel. Blood vessel, blah, blah, blah. B of x is twice differentiable, represents diameter. Okay, twice differentiable. Explain why there must be at least one value of x between 0 and 360 such that b double prime equals 0. I mean, I think this is going to be the same thing, except maybe actually easier because we go through and I'm going to look for places the mean value theorem guarantees that t prime equals 0. So, for example, I see 30 and 30. So t prime must be 0 somewhere in there. And then I see 26 and 26. So I think this is set up for us to actually like do it this way. All right, so b of x is differentiable, which implies continuous. Therefore, by mean value theorem, I mean, can you feel that this is basically the same problem? I hope so. B prime of, I don't know, C1 is b of 180 minus b of 60, 180 minus 60, which is 0, for some C1 between, that's an element of, that doesn't look good, element of 60. I actually looked up the other day, like, how can I improve my handwriting? And it's like practice, but you have to practice the right way. B prime of C2 is going to be B of 360 minus B of 240 over 360 minus 240. This is the same argument for some C2 element of 240 to 360. Okay, so now we do the same thing, but we do it for B double prime. So we're going to say B prime is differentiable. I mean, that's given, which implies continuous. Therefore, by MVT, ooh, bad V, B double prime of X is going to be B prime of C2 minus B prime. This one's a little easier because they're both 0, so like this is definitively 0. C1 equals 0 for some X, element of C1, C2, but like really just in general. So there's at least one value. I don't think we really need to write that. All right, there you go. This is a huge review of the vast majority of Unit 5 of AP Calculus, where we're talking about maximums, minimums, first derivative test, second derivative test, mean value theorem, reading derivatives, all that kind of stuff, increasing, decreasing, concave up, concave down. Anyway, I hope this was like incredibly helpful because it was a lot of work, and good luck.